Good morning. Welcome to Krishna's class. In this talk, we introduce the space L1V, which which is essentially looked upon as a normed linear space. Now, before that, we will introduce the integration of complex value functions. Now, we have an arbitrary space, measurable space X with a sigma algebra M and a measure mu on that. So this is designated by X as usual, X script M, and now we define L1. L1 mu defined as the set of all complex valued functions here valued measurable and integral mod x d mu is finite. Now we are now, so far we had been talking about non-negative measurable functions. Okay. And we have defined the integral for that. So the first task, of course, this definition does not involve that because we have mod f anyway, a non-negative real valued function. Therefore, this integral is well defined because if f is measurable, then mod f is also measurable. And therefore, this is well defined. So there is no problem about it. So we look at this class of functions, complex valued measurable functions defined on x. So you see that your f is defined from x to c. So you see that f has two parts, namely f its real part and the imaginary part. So both u and v are real valued functions. And then using this representation, we try to define the integral of f. So before that, we look at this class of functions, and now one of our tasks will be to define this integral. So we make some remarks. F measurable if f is a complex, as this we have earlier seen, the measurable function implies in fact what happens is f has the real and imaginary parts, both real valued functions, they are measurable. So f is measurable if and only if both u and v are measurable real valued functions. Now this is a real valued function, and you can see that if u and v are measurable functions, then measurable real valued functions, then square root of u square plus v square, which is non-negative measure value. That's what is written here. So, further remark. I'll write the second remark. Second remark is that members of are called Lebesgue integrable with respect to mu or summable functions. So these two remarks follow immediately. Okay. Now we define the integral of f. So we have used only integral of mod f, just well defined. Now we define integral of f. Definition. Let both u and v are real valued measurable functions defined on if f belongs to L1 mu, then we define integral over E to be equal to integral over E u plus d mu plus I times integral over E v plus d mu minus I times that's the definition. Where of course u is equal to, we have introduced this notation, and v equal to the positive part and the negative part of it. Okay. So this is u plus is essentially the maximum of u at x and 0. Okay. and u minus, this is the negative part of it, is equal to what you have. So you take minus u. Take minus u and then take plus. Okay, so that is u minus. Similarly, v and v plus and v minus are defined in this way. So these are all non-negative functions for which we have already introduced integration. So there is no problem. Okay. So these are the positive part, negative part. The positive part of E and the negative part of. So U plus U minus V plus V minus are non-negative real valued actually it is enough to say non-negative value, real valued, measurable, functions. Now further what we observe is the following. Just think this out. Now we have see u plus is non-negative, which is less than or equal to mod u. Okay, which is less than mod f, etc. Similar results hold for u minus v plus v minus. So now therefore what you get, you have integral u plus is less than or equal to which is finite. Okay, for L1 functions, now this is true. For every f belonging to L. And similar results hold for Now for measurable functions, this is some remark. For measurable extended real valued functions, for extended real valued functions, that is it includes not only the real line but also the infinity and minus infinity. We define integral over E but with one caution. The caution is that you see you have a minus sign here. If both are taking plus infinity or minus infinity, then see you are in trouble because this is not well defined. Therefore, we have to put that restriction on that. So we'll just put that condition there. At least one of them should be finite. That is the condition. So that the integral may be plus infinity or minus infinity. That is possible. Okay. Provided at least one of them is one of the integrals is finite. Least one of the integrals is plus the input and is finite. If this condition is not there, then you see you get some indefinite value. It's not well defined. Because you get indefinite value from it. That is the reason. Okay. In that case, belongs to minus infinity. Now we prove the following. Suppose and alpha and beta complex numbers. Then their linear combination that is one state. That means if f and g are L1 mu functions, then alpha f plus beta g belongs to L1. Further, what is that integral? That's what we have to say. Further, integral of in fact, this is true for any measurable subset E of X, E mu so this is okay. What happens is that the integration process is a linear action. That's what it is. Okay, that is what it says. Or in other words, we are asserting that L1 is a linear space. This means that this is something which you can prove. What it says is that it's closed under linear combinations. Okay, or integration is a linear operation. See, integration is a map from So what we assert is that this is a linear operation. Okay. Now we give the proof of this. First of all, we have already seen this, that if f and g are both measurable and real, and alpha beta real, then alpha f plus beta g is measurable. The measurability we have already proved. And you recall what we have proved is that if f is complex valued and measurable and g is complex valued and measurable, then f plus g is measurable. So also fg is measurable. This we have proved earlier. So the measurability is already done, taken care of. Further, we have integral over x d mu, and this is essentially equal to, now it's real non-negative situation. What does this mean? This implies alpha f plus beta g is L1. The first part, the first statement. And L1. That is alpha f plus this is what we have. Now we have to work out what exactly is the integral. So we shall prove this. integration. So we prove stage by stage, step by step. We do it in two ways. We prove that it is sufficient to prove that mu and integral over x alpha f d mu So instead of proving this at one stroke, we prove it in two steps. Okay. So let us first prove this. So we shall prove. That is the first one. What we do? Let h plus g. Assume or even extended real value. Okay, right? Doesn't matter. Now we have defined h should define as, then what we have to prove is that h belongs to L1. So how do we prove this? So you observe that h plus positive part of this is equal to h is h plus minus h minus. This is equal to f minus plus minus. Now this relation in turn gives the following, that is h plus f minus goes there, and then plus g minus equal to f plus h minus plus g plus. This is just taking all the positive terms to one side and the other one. So you rework this whole thing, and that's easy, straight away. Now you see, you can actually work out the integration of this. So they are non-negative functions, measurable functions. Therefore, you have the what is called linearity property of the integration force. minus. Similarly, integral over x t minus. So if you want, you can yeah, mu. Therefore, these two are equal. Now we reshuffle them. Now we rearrange them. By rearranging, we have we get we obtain so that is quite easy to, because what we already know is only for non-negative functions, and from there you have to go to general real valued or extended real value functions, and this is what we have. By rearranging this, you put all the h terms on one side, the other one on the other side, and then just combine them. Right. Now for alpha greater than or now we work the homogeneity. We have integral alpha af ft. I mean, that's easy to do. For alpha equal to minus 1, we now observe that observe that minus u plus. Okay, therefore we can work with this, right? Therefore you can actually work out this, what exactly you want to work. If alpha is equal to minus 1, we want to prove that integral over x because this you can write as f plus and f minus and then rework the whole thing and eventually you will get this result. Okay. Right? So now for I, then you can, next stage you can make the statement for all complex numbers alpha. Here we are we are assuming f is complex value. So these are real values. For real valued, we have already worked out the details. So then integral over x I f. This is equal to, what is I f? I f is u plus iv. Therefore, this is equal to minus this is this. Okay, and this you can write as, because of the previous one, you can pull this minus 1. Integral e dv. And then you can also this is which is equal to I times plus I times which is equal to I times now having proved this for multiplication with I, now you can work with alpha plus I beta. Okay, so in fact one can use this result, prove this for alpha plus I. Alpha equal to I beta one can prove this. Combine these results, we can prove that um, integral over x this is equal to, in between there are a lot of steps that you have to fill in, expand this, etc., etc., and then use these results. Which is equal to this is equal to alpha times this is true for every alpha belonging to complex number. So that is easy to, so it's just routine work that we use. Okay. Now we prove another result which says that the integral f d mu is finite. Okay. Next theorem. If f is an L1 function, this is what we want. So the proof of this theorem is also not difficult. So FT. Then it's a complex number. Complex number. Since Z is a complex number, where X is alpha belongs to C with alpha equal to 1, mod alpha equal to 1, such that alpha Z equal to mod Z. See, you have mod z to r. Okay. Now, how do you get r from here? So you multiply by, take alpha to be e to the power minus I. Then you have mod alpha equal to 1. Then so that's the standard result that you have. Let be the real part of alpha. Then you have u is less than or equal to alpha f d mu alpha comes from here. Okay, and this is equal to d mu, which is equal to which is less than or equal to ft. Okay. That's our goal. Therefore, the result. So this integral exists. Okay. So if f is L1, then integral over x f d mu is a complex number. Now we eventually prove the dominated convergence here. This is again of the type of result that we have earlier proved, namely we had a monotone convergence. A similar result, but instead of monotonicity, now we are putting in a new condition, a different type of condition. Okay. Right? In the monotone convergence theorem, we had Fn, we were considering only non-negative functions. So Fn was a sequence of non-negative measurable real valued functions with the property that it is monotonically increasing. Then we proved that the integration process and the limiting process can be interchanged. We are going to prove a similar result. Okay, but it's a different type of condition. We are no more assuming any kind of monotonicity. In fact, we are going to work for what are called complex measurable functions. So there is no question of writing a monotonicity condition in this case. But it equally well applies for the real case also. For example, why this theorem does not work for the example that we have looked at, that is Fn equal to chi n plus 1. We will see the reason. We will discuss it at the end. Okay. So we take the statement. Make the statement. Suppose the sequence Fn is a sequence of complex measurable functions on X such that the limit X is for each X belonging to H. If there exists a function G belonging to L1 mu such that these integrals are all bounded. These functions are all bounded. Mod X. For each X belonging to X, if it's bounded by a L1 function, so this is obviously a non-negative measurable function which is L1. Okay. Then F belongs to L1 mu and limit n tending to infinity equal to 0 and integral over X converges to or in other words, what you are asserting here is this is essentially limit n tending to or what we are asserting is that the limiting process and the integration can be interchanged in such a case. So here the condition that you have is that each Fn is bounded by a L1 function. Okay, before we go to the proof of this, which is fairly simple, we examine what happened. Considered earlier. See, we have defined x to be zero infinity, and of course measurable sets, and mu as Lebesgue question. With this, we have considered Fn to be equal to chi n cos. Now we have seen that in this case limit n tending to infinity is not equal to because f was identically zero in this case. Now we asserted that this was not true. Okay, in this case you see that the monotone convergence is not there. So that's what we have observed earlier. Now what if apply the dominated convergence theorem? Okay, is this valid? You see that in this case, you see that these functions are of this type. See, you have this is your x, and this is n plus 1. The graph of the function is this 1. This is so. This is a typical Fn. Is 0 here, everywhere else except here. That's why Fn is not monotone. But what happens if you try to apply the dominated convergence theorem? Now you see that, of course, it does not matter whether the functions are monotonic or not. So that aspect does not bother you. But what happens is, if we for a dominating function, then it is equal to 1 for every x belonging to infinity. That means g identically equal to 1. What about this integral over g? G mu is then equal to measure of x. Therefore, g is there does not exist a dominating function which is integrable. So that does not exist for these functions. That's the reason it is in this case, right? So if you try to apply either of the theorems, then there is a failure. Okay, right? So that's a very interesting example which works for all sorts of things, including the why strict inequality may occur in the case of the Fato's lemma. There also we use the same. It's a sort of multi-purpose example that we had, sort of omnibus example for our purpose. Nice example. Okay, now let us go to the proof. So mod f is less than or equal to g, and g is L1. F measurable and f belongs to L1. Since to G, Fato's lemma applies. And we get integral means this goes to 0. Okay. Therefore, this inequality is there, which can be written as integral over x 2g, because this is non-negative anyway, d mu, plus there's a minus sign here, and lim inf will become lim sup. Therefore, okay, so let me first write this lim inf minus take and pull this out. Now this will give you integral over x 2g d mu minus limit supremum n tending to infinity this gives the relationship between lim inf and lim sup. Okay, now you see this is finite, therefore you can cancel it on either side. Therefore you get 0 is less than or equal to minus of this. Okay, therefore get it's finite. By subtracting it, on both sides, the inequality the character of the inequality will remain the same. We get 0 is less than or equal to minus of that, or you have limit sup so you get 0 here, you just multiply by minus on both sides, so you get this inequality. This is less than or equal to 0. So that says the limit exists. So now applying previous theorem. To f1 minus f, we have integral over x goes to that's a proof of the dominant convergence here. I think that's a place where we stop. Okay, and maybe there will be a gap between the next lecture and this, because I am going to be away for about 10-15 days. From here So I will continue with this series of lectures after I return from my holiday at Bangalore. Thank you very much.